Marshall's a member of the MOM6 model development group at GFTL. He works on issues related to software development and infrastructure, including automated testing, bit reproducibility, and performance analysis of the model. Previously, he was at the NCI Supercomputing Center in Australia and was responsible for the efficient scalability of high-resolution coupled climate models. And prior to his HPC work, he studied the impacts of eddies on large-scale ocean currents. And one other interesting fact is, for a period of time, he also worked as a Game Boy programmer. Thank you for including that. Some of you know what I'm talking about when I say Game Boy.
It's a proud part of my career.
I think it's great. So take it away, and thanks again for being here.
Sure, thanks. So yeah, while this isn't directly connected to coupled models, I think MOM6 is a part of the kind of models we're all interested in. And so this was particularly an investigation into MOM6 performance. And so in particular, I wanted to kind of do a deep dive into how MOM6 was doing, and that's what led to this work. And I think it should have feedback into coupled models, into all the models. I'll show at the end that we are seeing some genuine improvement in potential production runs. But just kind of getting into it. So in my last job, as Rocky said, I did a lot of scaling analysis of coupled models, and I was actually part of a project that was given the very generic mission of, quote, improving the model. And you know, we kind of got in there and we did some work and we found a few things, but I got kind of very frustrated by that question, because how do you know when you're done? You know, you can optimize and then there's diminishing returns. And so the motivation was some work I did back then was to try to figure out the limits on how well we could do. So to define an upper bound on performance. So you can sort of construct a bit of an expression for the peak performance of a model. Sometimes it's called an iron law, but really it's a pretty simple law. So you can sort of set the performance by the number of cores you have available, the speed of those cores, and the sort of rate of vectorization, or sort of number of a concurrency within those cycles. So how many instructions can you do per cycle, with vectorization being the most predominant example of that. So you can kind of just look at those 3 bits and ask how well you can do. So I looked at scaling a lot in my old job, and this was sort of a figure. It was kind of a culmination of a lot of work. And so it shows the performance of the MOM5 model in their sort of high-res coupled model that they eventually released over there. And so the x-axis, so I'll mainly just talk about the figure on the left side. The x-axis is the number of cores, and the y-axis is the runtime per step of the model. So not the total runtime of any particular run. And so the 3 curves there represent 3 resolutions. The dashed line is sort of a perfect scalability where doubling cores halves the runtime. And I think it's a plot that's probably pretty familiar with everybody here. But I mean, the point is that the ocean models do generally scale very well, because they just don't have the kind of constraints that a lot of other models do. But they also have this feature where, of course, like all scaling models, they start to taper off. And I think in this case, there's quite a kind of unique feature, which is they all sort of taper off at the same point. So realistically, you don't really ever do better than about 1/10 of a second per step. And you can't see that on the 3rd curve because they wouldn't let me run anything bigger on our machine. But you do sort of see that the trend is consistent, where it's really starting to taper off. And it kind of illustrates that scalability is still our best advantage in performance, but it does have a limit. And that limit, by all appearances, seems to be getting worse, because if our steps time is not going down, but the step size is going down as we increase resolution, we're really, you know, CFL is putting us in kind of a bad position. So while we still should invest in CPU scaling, I think we have to kind of acknowledge that we have to start looking at other sources of performance. So the second term in that expression is shown on this figure. This is just showing clock speed, and clock speed was, of course, traditionally the source of performance, but around 2005-ish, that trend really just went to a sharp halt. And you can attribute it to things like Dennard scaling. But the main point for us is that clock speed really got to about 3 gigahertz and didn't really change much. There are secondary issues around clock speed, like number of cores active and things like that. But those are really just sort of engineering problems around the main point, which is that clock speed is really not a source of performance for us anymore. And so the final sort of term in that expression I showed is the degree of concurrency. And so even though clock speed stopped around 2005-ish, you can see on this figure, which is a plot of the spec FP benchmark. It's an industry benchmark, so take it as literally as you want. But there was still a trend in floating point performance, even though clock speed stopped. And I will say this is a composite of several tests, so it's not a perfect plot, but it does show that floating point performance did continue to go up for various codes, and there are Fortran models inside this benchmark, like ours. And the question is kind of, well, where were they getting that speed up from? And so revisiting that, if we go back to those three terms, the first one matters, but I'm not sure we can count on it forever. The second term, it doesn't matter. And the third term is really the one that I'm going to talk about here. Like, how are we doing on that concurrency? And is this something we need to invest more time in? So just to overview for the people on the call, what are vector instructions? They are when you stuff multiple numbers in a single register and then do some sort of manipulation, some arithmetic over all the numbers in that register. And crucially, you do it in one cycle. So assuming you get a decent pipeline and you can stage these things to be happening, you can do multiple arithmetic operations every cycle. So in this case, I did this on our machine GAEA, which has a 3.6 gigahertz. So if we were doing what are called AVX instructions, we could put 4 numbers into that register, and we could do 4 arithmetic operations per cycle, and at least have a kind of theoretical peak of 14.4 gigaflops. And that's not a made up number. Like, you can, technically speaking, flood the CPU with these instructions and get a number that is about 14.4. It's not necessarily a practical execution of that, but it does show that that is something achievable. An additional source of vectorization is FMAs. These are kind of a special case where you can do a multiply followed by an add all in one cycle. So it's kind of a doubling of the previous one, and those are vectorized as well. So there's an AVX FMA that can do double. So I've thrown some numbers up there that you can see, but basically it means we can get that 14.4 to 28.8. And I'll just comment that FMAs are not always used in production because they can change answers, although they're generally speaking more accurate than if you don't use them. But something to keep in mind, that they don't give bit reproducibility with the other case. And finally, we're still not done. So we've got this 4x speed up from what are called the AVX instructions, and another 2x from potential FMAs. But a modern CPU is actually not just doing one thing. It can do many tasks at once. This is just a little snapshot of what's called the execution unit of the Broadwell CPU. And you can show that it has these 8 ports on it, these arrows pointing downward. And you can basically be feeding it 8 what are called micro ops at a time. And they can all be doing different tasks. In fact, they can be doing different mathematical tasks. So you can have one doing an addition and another doing a multiplication, or you can have them both doing FMAs at the same time. So again, there's another hypothetical multiplier there. And another comment I'll say is that these can handle what you might call the bookkeeping tasks around your calculation as well. So the calculating of addresses and the loop indexes and stuff. So even those can be done at the same time. So you can kind of get this hypothetical super speed up of really, when you add it all up, about a 16 times speed up. And again, it's not like a made up thing. Like, you can actually hit the CPU with these numbers and get it. So, from a clock speed of 3.5 gigahertz, you can get over 57 gigaflops out of this thing in these very idealized scenarios. And so really, that's a useful starting point. But I mean, in practice, We want to ask, how does that look and how does that translate to our codes? So this is a figure here that that shows the performance of a kind of idealized arithmetic operation. I'm not going to break it completely down. I'm just going to call out some features of it. So the x-axis is sort of the size of the array, the length. I said vector length there. Array length would be a better term there. And the y-axis is the performance, the gigaflops per second. And so, and then you can see various colors denoting various quite simple arithmetic operations. So you could think of them as kind of micro operations within a more complex expression. And the sort of main, one first point to call out is that it does not achieve that 57 gigaflop number that I cited, but it does get kind of surprisingly close to it. It gets to about 24, and that's not true in all cases, but it's probably, you know, it certainly depends on its ability to leverage those things like the FMAs. The other striking thing, of course, is that as the array gets larger, a lot of that diversity and performance just sort of collapses down onto itself, and you see that what was about 7 or 8 different levels of performance really drops down to about 3 as the array crosses the threshold. And just very quickly, I'm not going to do this in detail, but I want to show my home machine, which is an AMD Zen Plus style architecture. And it's quite different. I want to call out that it has a lower peak, but it's doing a much better job of that cache, you know, the issue that I showed, where it's sustaining that performance over a much larger range. And I'm not going to dwell too much on that. I want to focus on the machine that we're using, but I do want to call out that this is kind of a good example of the Intel versus AMD trade-off, which is Intel does the best in the best way, but AMD seems to be doing a lot more consistency with its performance. So we can understand those drop-offs on this figure. So I've drawn these dashed lines denoting the cache hierarchy. So I assume everyone here is familiar that CPUs have cache levels. There's the L1 cache, which is connected to the registers. That is fed with a larger and slower L2 cache, which is itself fed by an even larger and even slower L3 cache shared across cores. And finally, it's all backed up by the RAM on your motherboard. So essentially, as the array gets larger, it no longer fits in these cache levels, and that's sort of indicating that we can't provide the numbers fast enough to reach what you could say is a compute bound calculation on the left side, and we gradually progress towards a cache bound and finally a RAM bound calculation. So I wanted to show this figure to highlight it's really in a really what I think is a nice graphical way exactly what the phrase RAM bound really means. And it really means that you just, you know, it's a continuum, and then it drops off into these regimes. And so this figure, I don't need to talk about it, but it does show in detail what's going on. That you do see these two other expressions doing a little bit better. Those are basically because they're doing additional scalar operations and they're benefiting from FMAs. But so they don't, you know, basically it's a question of how much data do you need to do your work. But in general, the drop off is very real. So, but we can take that plot and sort of construct what is a little bit of a rubric to quickly diagnose whether or not we're RAM bound or cache bound or compute bound. And so it's obviously, even on this table, the numbers vary, but it does show you that if you're getting about a gigaflop per second or less, you are almost certainly in a RAM bound state. Whereas if you're starting to get higher, so 2, 3, 4, 5 gigaflops, you're probably residing somewhere in the cache. And then finally, if you're getting very large numbers, like over 10 gigaflops a second, that means that you're doing something right and you are starting to get one of those very fast compute bound calculations. So, so that's a pretty long intro, but it sets up the numbers that I'm going to show for MOM6. And so the thing about vectorization is these are all things that are set up at compile time in your object code. They're not necessarily aware of the size of your problem and the CPU parallelization. So in a lot of ways, you're just as good looking at this on one core as you are on 1,000, with one exception that I'll get to at the end. But in this case, this is a very small one CPU job. It's sort of set up to resemble a typical sector of a quarter degree high resolution 1,000 core job. So in this case, it's 32 by 32 points. It's got 75 levels. So it's about 2 to the 16 in number of fields. And in each horizontal level, it's about 2 to the 10. So if we wanted to go back to that figure here, we can sort of see that there's some idea or hope at least that the 2D operations will be much more cache and compute bound, whereas the 3D operations will be sort of at least in that L3 regime and possibly even worse. So it's a very short job, but I feel like I've run it enough where I have confidence that the results don't really change, particularly with respect to the flop rates. And some of the things that are turned on are things that impact the performance. They don't necessarily impact the utility of the solution. Just an example, we are running split barotropic. So there's the barotropic solver alongside the full 3D solvers. We have a CONCURRENCY by harmonic, which I call out in particular because in addition to being a complex calculation, it involves a very expensive square root. We have full thermodynamics on, which includes a right equation of state. And I call that out because that is a very complex expression with a lot of calculations in it. And finally, there's something in here. It's written here as bounded Coriolis. It's a limiting of the Coriolis terms relative to its neighbors. I think I'll leave it at that. And finally, we are not running in AL mode. That just happened during the testing. I think you could just as easily repeat this with AL on and you'd find a whole new set of interesting results. So I'll quickly review the tool that I used to get these numbers. I used a program called PERF, which not everyone is a fan of, but I am a big fan of. It came out of development and evaluation of the Linux kernel. And it's still, to build it, you have to get it from the Linux kernel source code. But the reason I quite like it is, if you can see in this little snapshot that it really gives you a breakdown of the symbols in your code. So basically, you don't need to go in and assign specific timers and define events. It just grabs every symbol available, and excuse me, and it gives you a very nice breakdown of the runtime of those. And you don't have to apply any special wrappers or anything to use it. It just works with the, compile with the G flag, and you get all those symbols. And I'm showing here the runtime, but you could use this to gather all sorts of metrics, not just times. You can use it to get flops. You can use it to get branch prediction numbers, like whether or not you follow an if block. You can use it to get very explicit numbers on cache usage, whether the number of rates you hit and miss these things. I will say in practice, those are very, very difficult numbers to interpret. And so I just stick with the flops and times here. But the important thing is they're available. And another thing I'll point out, if you can see on the text, there's a reference to libc. And that's another thing I very much like about this tool is it doesn't restrict you to the program you're running. It will look at the totality. It will give you stats on allocations in libc. It will give you times in the kernel. It will give you times in MPI or even netcdf. It will give you the full picture on where you spend your time. And so that's why I'm quite a big fan of it. And the other reason I'm a big fan of it is it shows you the assembly code. So this is a line sampling profiler. And it tells you not only how much time you spend in each line, but how much time you spend in each assembly instruction within that line. And I think that's particularly important for us because it's telling us whether or not our code is vectorized. And you can see here, this is a very obvious hotspot in one of our functions. And I will go over what those instructions mean a little bit. But don't worry, there's not a lot of assembly. Just for starters, when you run perf, you typically start off with a perf stat, which gives you global metrics. And I just want to call out a few things on here. So one thing is that we're running at quite a high frequency here, 3.7.5 gigahertz. This is my home machine, by the way. That's why it's higher than 3.6. The fact that it's so close to the peak shows that we're running this thing at our full turbo frequency for almost the entirety of our run, which is a very good sign. Another number interesting here is that we spend half our time in quote stalled cycles, and this is basically where the CPU is waiting on information. So this is going to be a common theme here, that we spend a lot of our time moving data around and not so much time actually computing numbers. In this case, 54% is actually a pretty good number, despite how bad it might seem. But anyway, you can see all these things. The last number I want to call out is the flop rate. So we are seeing here a flop rate of over 2.5 gigaflops per second. So I mean, I think that's a good number. So, you know, we're already kind of starting at a pretty good place with MOM6, at least this particular experiment. Like we're not in that RAM bound regime. We're certainly at least spending our time on cache operations. Now, we can further break this down by function. And so if we want to kind of sweep through the functions in the model, what we can see, so this is, there's one slightly unintuitive thing about this plot. I put flops in time on the same axis. You can either take that as a benefit or very confusing, but the blue bars represent the percentage of runtime and the orange bars represent the flop rate. So what you can kind of see is that overall our runtimes are pretty consistent. We have quite a long tail. We do have 3 rather large ones that take up about 10% and 7% of the runtime. But once we get past it, we get kind of this very long tail of about 4%, 3%, 2%, and we stay like at 1% for a long number of functions. So what we find is that we're actually kind of in a, this is a good sign and a bad sign. It's a good sign that there's no obvious bottleneck in our function, but it's bad where if we want to do work to improve it, we do need to kind of sweep through a lot of functions. So another thing I'll call out is that the slowest functions do have the lowest flop rates of about 1 gigaflop. So they are most certainly RAM bound. As we move down to the other functions, though, they sort of hover around 2 or 3 gigaflops. So it's a good sign. We're not really in a RAM bound state for the bulk of the functions. And the last one is this density DZ right, which is the equation state. It has a massive flop rate of 12 gigaflops, and we will get into that. So I will go through this I'll try to get through this quickly, but basically what I'm going to do next is call out a few of those sections and sort of explain what we think is wrong with them and what we did to improve them. So I'll start with the horizontal viscosity function, which I believe was the second slowest function on here. Yeah. So, okay, there we go. So what we found, so basically PERF told us that this function was a problem, and it even called out particular lines. So what we ended up seeing was that we had this very large if block, and it was doing lots of calculations inside it. This is calculating the magnitude of the shear and involving a square root. Then it's doing it's checking whether or not the leaf viscosity is on, and it does some more work there. It's checking if we're bounding the coefficients, the viscosities. It's doing another thing and another thing. And so basically we had this loop with an enormous amount of conditionals inside it and an enormous amount of operations which didn't really have a lot to do with each other. And so if we look at the assembly, we see it's using AVX instructions, but they are not vectorized. It is doing 1 arithmetic per cycle, even though it's AVX. So an AVX test would not have even detected this. You can only detect this by looking at the assembly or the flop rates. And just to show the code here, if it ends in SD, it means it's a serial double precision. If what we want there are the PDs. And then another thing I'll call out quickly is that we also noticed that it's spending a lot of time moving values onto the function stack and back to the registers and forth and so on. And it's spending a lot of time moving data and not a lot of time solving. So what did we do here? So what we did is we took this function and we, instead of having it as one big if block, we broke it up into many small if blocks. And the second thing we did is we moved those if statements outside the do loops rather than inside them. So by moving them outside, we signal very clearly to the compiler that we don't need to do this every iteration. Now, occasionally you'll find compilers are smart enough to do that for you, but in this case, it was not smart enough. And we really had to do it. And I suspect it had to do with the complexity of, I suspect it had to do with the number of operations inside the if statement. So you'll see here, this was one thing we moved out. This is another block, a third block. I'm not going to go over what they are, but basically you could see that we've turned this into a lot of nested if statements. The other main thing we did is we promoted a lot of those scalars in the old if block into 2D arrays. Normally, I would not encourage this, but in this case, it was a win. It was required to make us split the blocks. I think this is a case where you come back and try to find a way to eliminate those scratch arrays. But in general, you're much better off vectorizing an array than you are not vectorizing a bunch of disparate scalars and arrays. So how did we do? We see we did get a speed up here. So on GAEA, we went from a bit over 2 seconds to a bit over 1 second. So a pretty significant speed up. Nothing revolutionary or game changing, but a very dramatic speed up of that function, and a very similar one on the AMD, on my home machine, basically. So we want to revisit this. So now we want to look at another section. So we'll look at that CORIOLIS advection, and that involved that bounded CORIOLIS operation I mentioned. That involves a lot of inequality tests to limit the value. And again, you're doing those inside a do loop, and they are quite expensive. But that was one issue here. But we had another issue here. Here we compute the maximum value of the product of the vorticity and velocity here, and we store it in this array called max and min FVQ and FUQ. And then for 200 lines, we do a bunch of other work that has nothing to do with it. So what happens? Well, it has to put that into RAM, it tucks it away, it does a bunch of work, and then when we come back to the work, it's got to pull it all back. So this ends up adding a bunch of memory movement that is really slowing us down. So in this case, we fixed it by just taking those two blocks, and luckily they didn't depend on any of the intermediate work, and we were able to just merge it in. So in this case, we completely removed an array, 2 arrays, turned them into just scalars, which meant they could be held in register, and we basically got a speed up here. Now, Intel had a modest speed up, and AMD had a quite large speed up. I won't explain in too much detail here, but I want to give a bit of an explanation here. This is because there is an AVX instruction to do masking to help with some of these inequalities. And Intel, that instruction is very fast on an Intel CPU and very slow on an AMD CPU. And the compiler is smart enough to know better to not use them on AMDs, but to use them on Intel. So what you find is Intel was not suffering so much from some of these issues. And so that's why the speed up here was more modest, whereas the AMD was a much more substantial one. So a third example is the barotropic solver. That was the most expensive function in our profile. And to do this, this was an interesting one. I couldn't find anything wrong with the code, but it was refusing to vectorize. So I had to look at what's called the vector report. This is a example of a function that is being sort of well analyzed. So if you don't know this, what Intel does, yes, there was a question from Nikki. I use the Intel compiler, same version on both of these, 19. And I think I just got another question asking about the architectures. Let's leave that to the end. I'm just going to say it is an issue, but not as much as you might think for this for these numbers I'm reporting. So what you can see is this is a report that is sort of being well vectorized. However, as I read through the report, they just sort of stopped, and about 1,500 lines in, it just was just saying, I'm not going to do this anymore. It had this no optimizations reported. And so I found an interesting comment here saying some were skipped due to constrained compile time. So basically, our function was just too big. Our function was 2,000 lines, and it's just said, I can't do this anymore. So with the way Intel optimizes, it actually runs lots of little micro tests against your code to determine whether or not what the best decision is. And it's just giving up. It's just saying your function's too big. And I think this is an interesting case of software engineering where, we're always being told to keep our functions small, but I think a lot of us kind of roll our eyes and say that's just style. But I think this is a very pragmatic case where it is very important to keep your functions small, certainly smaller than 2,000 lines. So what happened? Well, we turned on the override, and we did again get a somewhat significant speed up. On the Intel, we got about a 1.5 speed up, and on my home machine, about a 1.9. So of course, what we properly need to do here is not have such a large function. We need to split that up into pieces that the compiler is willing to analyze. And it does show that, we have a very we have a relationship with our compilers. They're not like predictable machines all the time. So just as a final example, which is less of an example than more of a counter example, this was, I believe, the third most expensive function, the vertical viscosity. So one point here is that these are loops, but of course they contain that dreaded if statement inside the loop. This is a do-I loop. In fact, it's checking to see if we're over land or not. And it's making a very reasonable question of whether or not we should be doing this if we're over land, because there's no point. However, there is a point, because CPUs operate on pipelines. You need to be doing the same thing over the same data set as much as possible. And when you constantly shift gears, and if you break that contiguity across memory, then you start to break those pipelines. You make it very difficult to efficiently populate the caches from the RAM, and you really get a breakdown. So let's question whether or not that's a good idea here. So in here, I broke that loop into several small loops. There was a bit of array promotion, and so we ran it. And so this is an illustration, maybe a popular one with some of you, on why you should do this. Well, arrays are not multidimensional; they are one-dimensional entities, and so the best way to keep your performance is to stay on that 1D array as long as consistently as possible. So how did we do? Well, the flops did great. The vertical viscosity function overall went up from 1.3 to a 2x in terms, to 2 gigaflops per second. And one particular function inside there, which comprised a lot of the time, went up from 2.5 to nearly 6 gigaflops. So on the surface, an incredible number. However, when you actually look at the times, the result was less than impressive. What we see is basically there was really no real net change on the Intel machines. It's just a bit of a reminder that it's not about flop rates do matter, and they are a great metric of how well you're doing, but they are not the whole story. You really do need to go to the time in the end. In fact, this one, I'm still on the fence about it, so I have not actually submitted it yet. So this is a change that we are still sort of trying to decide what to do with. And finally, I will just quickly posit on why the equation state was so fast. Basically, it's because it was doing a whole lot of math. This is one little snapshot inside that function. There's another one down here. There's not very many array accesses. There's just calculation of pretty complex polynomials and other expressions to get the density, I assume, and or something thermodynamic. And so it just shows that this is what you need to do to get the best performance. As long as you're calculating numbers, you're doing great. And it's just a bit of a reminder that the real issue that dogs us is getting the data into the CPU. So kind of summing up our progress, we did see that we were able to get almost a doubling of the BT step. And I apologize, that number, I think these might be the, well, let's just say these are the numbers we got. And so what we see is we got quite significant speed up of BT step and horizontal viscosity, as well as and modest speed ups in the fine coupling coefficient and Coriolis advection. And otherwise, the rest were sort of, you're seeing the variability of noise. But if you sort of tally it all up in our model, changing those 4 functions and making sure they're vectorized gave us a speed up of about 10%. So I think given that we only looked at a few of the functions, I think there's still quite a few wins ahead of us. A good question is, I did this on one core, and does this translate to a proper parallelized code? And the answer is mostly, largely speaking, yes, but not entirely. So this is comparing it to a 1400 by 1000 model with 1000 CPUs. And so we do see that the speed up in the horizontal viscosity actually got better. It's 1.87 versus 1.75. And that's because we are getting out of that RAM bound limit. So even though we're probably adding overhead with communication, we're also, when we're running in parallel, the ranks, the MPI ranks are often sharing the RAM with other ranks. And so that is further limiting our access to the bandwidth of that RAM. So being able to move calculations out of RAM and towards the L3 cache, and if not higher, really does have a significant benefit to us. The other two functions, the speed up was more modest, and I believe it is because we were already sort of operating within the caches for those operations. And so what we're kind of seeing here is the vectorization speed up minus presumably the overhead of being on a parallel code. So so that's sort of summing up the changes we've made. And the question is, we don't want to lose these changes. Those changes happen because feature creep basically added additional checks, this feature, that feature, and it bloated our do loops with more and more calculations, and it really sort of happened without our awareness. So what we're trying to do is come up with some way to start tracking this and getting some feedback in both a short-term and a long-term way. So this is a bit of a snapshot. I'm not going to, I can click this and it'll go to a link, but hopefully you can see that what it's doing is we're basically parsing all the FMS clock runtimes that come out of this. And what we do in our CI is we do a bit of a regression test where we compare any contribution to the model to the current state of our development branch. And we basically, what we do is we check that there's no answer changes. This is doing the same thing, except we're comparing the runtimes of two different experiments. And we're doing that not just in the total, but across the various FMS timers. Now, I found in practice, I'm doing this currently, this is GitLab. We're doing it actually on GitHub Actions at the moment. I found GitHub Actions runtimes are very wild. They vary from, this particular one goes from 30 to 45 seconds. So at the moment, I'm not quite sure how useful these numbers are in GitHub Actions, but they're sort of more putting a template for what we want to do on a machine where we have more control. But we're not done there. I've actually managed to get the perf output also onto GitHub Actions and to do a similar diff here. So we've been able to grab that information and with a bit of suffering, but we are basically able to repeat this with the perf metrics. So at the moment, what I'm not sure how to do is to get more sophisticated metrics. I only know how to get the runtime out of perf on GitHub Actions. But in principle, we could use this same framework to start tracking and reporting flop rates alongside of times. And again, we compare this percentage, and basically what we hope to do is get like a call out when that difference is egregious, like a doubling or maybe even a halving of the runtimes or the flop rates. And again, we're still looking at how to do this in production, but one thing I'm currently doing is starting to automatically log these timings into a database so that we can sort of produce very long-term historical trends on the performance of the model. Because I mean, if something adds a small difference, then we're very likely to not even notice it. But if we track these things over, say, a month or a year or several years, we really can have like a very nice history of how the model is doing performance, and we'll start to be able to check these things out more quickly. So yeah, I went a little over the time Rocky gave me, but I'll wrap it up there. So we are now actively monitoring flop rates alongside of times, and we do see that the flop rates currently are actually a little better than I would have guessed. They're actually running reasonably well in terms of, we're not terribly RAM bound. We are doing a little bit better than 2 gigaflops. And we've also managed to find some rooms for improvement and get some speed up of some functions of nearly about doubling. And we've also seen that these numbers do hold to some degree in larger jobs and should also translate to a coupled model, one would hope. And yeah, and I guess finally, we hope we can really integrate this sort of tests into our automated testing and really keep track of it. So I will leave it there. I saw there was at least 2 questions, one I had to bleep over, but thank you.